Okay, in this figure, we see another example of a two-variable data set made from a mixture of two sine waves. Each mixture has different amplitudes of the two sinusoids and some noise. And if we look at a scatter plot comparing time points of x1 and x2, we see that clearly there is some correlation between the two data sets. In other words, knowing the value of x1 would give us a range of possible x2 values. So these data sets are correlated. The correlation coefficient is 0.77. So after we rotate the data set, we find the values are no longer correlated and we get this scatter plot. But the values, as we discussed before, are still mixtures of the two sources, just a different type of mixing. And so these are not any more meaningful than the original variables. So in this case, you really do need two variables to represent the sinusoids. So one thing to think about is that just because data sets are uncorrelated does not mean they're independent. And the previous case gave us an example. We'll look and see where two data sets are uncorrelated. Now let's look at another possible example. So if two or more variables are statistically independent, they are also uncorrelated, but the reverse is not necessarily true. So let's look at the next slide where we'll get some information that two signals, or we'll get an example of two signals that are technically not correlated, but they are related. So here are two variables, x1 and x2. Clearly you can see that there's a linear relationship between the two, and they have some noise added. So these are uncorrelated but not independent. Here's a scatter plot, and you can see the scatter plot, x1 and x2, have a relationship that is like a circle with some added noise that accounts for the fact that there's some width to the circular function. So the easiest way to implement principal component analysis is to use a technique called singular value decomposition. And this is basically a matrix technique that looks for the eigenvalues of a series of a matrix that would give us the original data set. So in this example, X is our original data set, and S is a diagonal matrix that contains the square root of the eigenvalues, and U is our principal components matrix. V is the orthonormal version of the principal components matrix. In this particular example, the author is using some notation that comes directly from MATLAB because he's using MATLAB's implementation of singular value decomposition. So there is some assumption that you have a little bit of a linear algebra background. So once again, X is our data matrix. It's an m by n matrix, and what we're really doing is we're decomposing it into three components. One is an m by m orthonormal matrix. Remember, orthonormal is orthogonal that has been normalized. S is an m by n diagonal matrix, and V is our n by n matrix that would contain the principal components. Now, MATLAB has built into its SVD routine the ability to minimize the size of V automatically by eliminating some components that don't make a significant contribution to the data sets. So U provides a transformation matrix that basically accomplishes rotating our data set. It'll produce a rotated data set that has zero covariance. S is a covariance matrix of the new rotated data set, and it's a diagonal matrix where the off diagonals are the variances of the new, where the diagonals are the variances of the new data set. Now the off diagonals will all be zero because our new data set is uncorrelated. So if you square the diagonals of this covariance matrix, you get the eigenvalues. And the eigenvalues are ordered by magnitude. V has columns that are characteristic vectors or eigenvectors. When they're scaled by their respective variances, they become the principal components or the new data set. So the eigenvalues are related to the variances of the principal components, and they're a measure of how the associated principal components importance. In other words, how much of the total energy does it represent? They're given in order of magnitude. So the first principal component is going to account for the maximum variance possible in a single component. The second component accounts for the maximum of the remaining variance, and so on. So the last principal component will contain the smallest amount of variance. Now, this is not uncommon. A lot of multivariate operations involve data rotation. And if we just thought about two dimensions that contain an x1 and an x2, we basically can achieve a circular rotation of angle theta by implementing the following transformation, where we're transforming x1 and x2 into y1 and y2, some new data vectors. And this, if you look at this as a matrix multiplication problem, then the rotation matrix would be the coefficients multiplying x1 and x2. So cosine theta, sine theta, minus sine theta, and cosine theta. So this is just an example of a rotation technique that we can visualize because it's in two dimensions. And here's a MATLAB example that you can find from the textbook. Basically, we're just implementing that previous set of equations, and you find that before rotation and after rotation, you've basically accomplished rotating this data set by 45 degrees. So the point to put this example in here, it seems a bit out of place, but the point to put this example in here is that when we use two dimensions, it's something we can easily visualize as compared to many dimensions. So in MATLAB, singular value decomposition is implemented using the SVD routine, where X is our original data set, U, S, and V are the matrices previously defined, and then this command econ basically will reduce the size of the S matrix and the V matrices considerably. So if econ is used, there is going to be some automatic reduction of the dimensionality of the data set in this MATLAB routine. We can then determine the eigenvalues by taking the diagonal of the matrix X and squaring it. And then the principal components are obtained from the columns of the matrix V. It's common to normalize these principal components by the variances so that different components can be compared. There are a number of ways to do this. One way is to multiply the eigenvector by the square root of the eigenvalue, in other words, the variance, because this will give rise to the principal components that will have the same value as a manually rotated data array. So the eigenvalues, remember, describe how much of the variance is accounted for by the principal component and if we really need that principal component. So what you do after you do this reduction is you now take your eigenvalues and you order them by size. And if you get an eigenvalue that is either 0 or close to 0, then basically what you can say is the principal component associated with that eigenvalue does not contribute much to the data and can therefore be eliminated. So because this component would account for only a small amount of the variance of the data. So basically this tells us the effective dimension of the data set. So I guess the question then becomes, how small is small? So that you can remove an associated component from the data set. So there are two popular methods. One is you would take the sum of all the eigenvectors, which would account for all the variance, and then delete those that fall below some percentage of the sum. Another way is to plot the eigenvalues in decreasing order and look for breakpoints in the slope of the curve, and then throw out everything that's above that breakpoint. So a plot like that is called a scree plot. And here's an example. You can see, it's not super easy to see, but you can see there is a little line here where we're plotting magnitude of component. And then at this point here, at component number 2, we see a little bit of a break. And then at component number 3, this curve really flattens out. So after 2 components, we pretty much get a significant flattening of this plot. At that point, we could say, okay, at this point, we've probably accounted for most of the components that describe the original dimensionality of our data set. So here's an example of a physical situation where we had basically 2 original data sources. And then these sources are mixed using a linear kind of mixing, and noise is added. And so what we end up getting are 5 variables composed of the 2 sources and the noise. So this would simulate a situation where you had 2 physical sources of data, and then you have 5 measurement probes. And so you're getting these 5 data channels that really are composed of these 2 sources. So let's see what happens as we do the principal component analysis using SVD, and then we'll look at the eigenvalue ratios and generate a scree plot. So this is done in MATLAB. So the first thing to do is to generate the data, and you can see there are just some linear combinations used of the data y and the data x, where y is the sawtooth and x is the sinusoid. There's some noise added here, different percentages, and then one of the signals is noise only. The data are centered, the mean is subtracted. So here are your 5 mixed signals. So the next thing to do is to find the eigenvalues and the eigenvectors. So we have our U matrix, S matrix, and our principal component matrix obtained by doing single value decomposition. And then once the single value decomposition is done, we then take the diagonals of the S matrix and square them, and then look at a plot of that in decreasing order of magnitude. After that, we'll also calculate the eigenvalue ratios so that we can print out a correlation between principal components. So here is a scatter plot of the 2 principal components, and you can see that basically after singular value decomposition was done, MATLAB returned that there were 2 principal components, 1 and 2. You can see they're uncorrelated. There's no functional relationship of any sort between these 2 variables. Here's the covariance matrix of the principal component. You can see now all 5 component matrices or all 5 components are uncorrelated because we don't have any off-diagonal elements. And now also notice that these are in descending values. Notice the first one is 0.43, then 0.20, and then we have a pretty significant drop-off. So this is basically the matrix S that's produced by the SVD routine within MATLAB. So it's a covariance matrix of the principal components. So here's the scree plot where we're plotting component number and its eigenvalue, and you can see that clearly by the time we get to the 3rd component, there's a break in the slope here. So we could easily say that the first 2 components are significant principal components. The remaining 3, because they don't contribute much to the variance, are much lower as far as bringing any new actual information to the data set. So we could actually reduce the data set to the 2 new principal component values. So we've reduced the dimensionality of our data from a 5-dimensional to a 2-dimensional data set. And this is significant. Now here is the result of the principal components that came out of this routine plotted, and let's compare that to our two original components. And so while the data sets are uncorrelated because of the result of this SVD and the value of the off diagonals in the S matrix being 0, they're uncorrelated, but they're not independent because clearly these are still mixtures of these two original components. So the key takeaway here, okay, is, let's go back. The key takeaway here is that principal component analysis is a very good technique to use if you want to reduce the dimensionality of your data set. It is not a good technique to use all the time if you want to unmix two signals or more. So while you will eliminate unnecessary dimensions in your data, you will not unmix the signals. That requires a different technique. So the technique that we would use there would be independent component analysis. So the reason to give you a preview of the independent component analysis is to say this does not mean, if we're going to use this more powerful technique, it does not mean we throw the principal component analysis technique out the window, because it's the principal component analysis technique that's often run as a pre-processing step. So we will run PCA as a pre-processing step in order to reduce the dimensionality of the data set before we do anything else to unmix the signal.